correct answer here is 40.00%. If you got 39.99, that'll probably work, but again, 40.00. Remember, when you calculate percentage is always the part over the whole times 100. So if you're going to calculate that percentage, you will need to go ahead and add up the atomic masses. You should find that carbon accounts for, I believe, 72 grams on this one. You'll divide it by the whole amount, which is 180, and then you'll take that result and multiply by 100. Any questions? Okay, next one. There are, oh, I put in 13.2. I think I wrote 13.3 for you. I forgot to write it on here. It is 13.3. It is 13.3. But I forgot to update the number on here. So calculate it based on 13.3, not the 13.2 that I have written. This 13.3, I think, is what I gave you, isn't it? Yeah. Okay. So we'll give you about a minute to get your answer locked in here. And if you're not sure what you're doing, you should be consulting with a neighbor. Preferably not staring into empty space. Calculations based on 13.3, not 13.2. So we'll go ahead, give you about 20 seconds here, get your answers locked in, please. Okay, and we're going to count down. 5, 4, 3, 2, 1. Correct answer here is 917. 917. Some of you are not reading the fact that you're not supposed to be putting in units on here. Okay, and 3 significant figures. If you look at this one, this is not 3 significant figures. This is given in 3, I don't know if you can see that number. That's put in 3 decimal places. So you're requested to put it in 3 significant figures. This is 3 decimal places. On the exam, this would not receive full credit. Likewise, this would not receive full credit here as well. So any questions on this one? Yes, I can do that. Yep. So if we want to calculate this one, we start with the, let's see, this was the moles or the grams. We're starting with the 13.3 moles on this one. Okay, so if we have 13.3 moles of lithium nitrate, we want to get over to grams of lithium nitrate. What sort of conversion do we need to get from moles over to grams? What is that called? Anybody remember what that conversion is called? It was in your Socrative question coming in today. It's called a molar mass. It's called a molar mass. And the molar mass is the number of grams contained in 1 mole. So we need to know the number of grams of lithium nitrate contained in 1 mole of lithium nitrate. And how do we find the number of grams contained in 1 mole? Atomic masses, right. So we come back to the periodic table here. We find lithium. We see that lithium has a mass of 6.939. We have 1 nitrogen at 14.01. We have 3 oxygens each at 16. We sum those together. And what do we get? I don't have that number. Anyone have it? 68.949. And of course, if we're following significant figures, we put it 68.95. But either way, You can go ahead and plug it in and calculate your answer. Really, the only rounding that matters is in the end, not in your end. So we want to put this calculation in here. What do we put in the denominator? 1 mole. And in the top we put in 68.949 grams of the lithium nitrate. And then of course the moles of lithium nitrate cancel out. We wind up with 917. Okay, take care of it for you. Okay, anybody else? Okay, remember this now, that this molar mass, you'll need it in the last one. So we'll go ahead and do the next one. Oops, looks like I forgot to update the number in this one as well. So this should read 13.3. It should read 13.3. So we're now trying to find this answer. Figure out how many moles there are in 13.3 grams. Not the 13.2 like it's written in the Socrative. And forgot to update the number. Is this called brown nosing?
No, it's funny.
Ah, okay. Because that's what we call the people up front. All right, let's get your answers locked in. We'll give you about 15 seconds here. And we'll count down on this. 5, 4, 3, 2, 1. Correct answer is 0.193. 0.193 is the correct answer. I see some have 917 in there, but what you've forgotten is that this one's kind of just the reverse of this one. What we're starting with is the 13.3 grams of the lithium nitrate. We've already calculated that molar mass. We're trying to get to moles of the lithium nitrate. So this time when we put the conversion in, what do we put on the bottom? All right, the 68.949 grams of the lithium nitrate. And on the top we put in 1 mole of the lithium nitrate. Then what will happen here is that the grams of lithium nitrate cancel out, and we wind up with that answer of 0.193 moles of lithium nitrate. 0.193. Okay, this will take care of the mole concept for us here. Any questions on the mole concept? There's actually one more thing I want to go through it. Anything that we see up here today that we have questions on? Okay, then let's go back to our notes from the other day. I realized when I say the other day, this would have been from Tuesday. In here, let's see which one we were doing. Here we go. We had the ammonium nitrate. We were talking about this a bit. And for the ammonia, and when we were doing these, just like the very first problem here today, we were asked to find the percent by mass composition of carbon. Well, let's just say that you were asked on this one, and I'm going to just copy and paste this whole page over for today if I can figure this out. Let's copy this so we can put it in today's notes. There we go, we'll paste it. And if we're to follow through on this, let's say that you were asked to find the percent by mass composition of ammonium nitrate. Now if you look through here, is there an element specified?
No.
There's not. So if there's no element specified, what do you suppose we do here? Exactly. We find the percentages for all of them. So again, if you simply see percent by mass composition, and there's no element specified, then you calculate the percentages for all of them. We already calculated the percentage of nitrogen on this one as being 35.00% nitrogen. If we wanted to find the percent of oxygen on this one, we could come back to here and see that we have the 48.00 grams of oxygen. We divide it by the whole amount, which is the 80.05 grams of the ammonium nitrate. So again, 48.00 grams over the whole amount, which is 80.05 grams. And multiply that result by 100. If we do that, we wind up with an answer of 59.96% oxygen. And so now there's only one element left. And now one of the ways we could do the element that's left that's hydrogen is the same way. That is, we could take the amount that is hydrogen, which is the 4.032, and divide it by the 80.05 times 100. What is another way, if we don't do it this way, what is another way we could obtain the same answer for this one? Exactly. We could take the two answers we have and subtract them from 100, because of course the percentages should add up to be 100%. So we could start with 100% here, which of course is going to be 100.000 on into infinity. So simply writing 100, we're assuming then that that's an exact value. Would subtract the 35.00, would subtract the 59.96. So again, 100 minus 59.96 minus 35, and we wind up with an answer of 5.04% hydrogen. So I forgot to show you this here the other day. When there's no element specified, you calculate the percentages of all of the elements present in the compound. So at that point, this does take care of everything that we plan to cover with the mole concept. Are there any questions on the mole concept? All right, going once. Nabila?
So there's three conversions we need to know for the mole. We have to know how to change it from mole to the number of molecules, and also how to find the mass of it, like grams.
Yes. Thank you. Usually I don't sum this up till we get to Chapter 8, because we'll be revisiting the mole concept when we get to Chapter 8, but it'd be good to sum it up right now. So some conversions we might be required to do would involve converting from moles to molecules, as you suggested, or it could be grams to molecules. And remember, it's not always molecules. Instead of molecules, it could be or atoms or formula units. And likewise here, it could be the same thing. We could be asked to convert grams to moles. We could go from moles to grams. And then I guess we could take these top two and change them around as well. We might go from molecules to moles. Or we could go from molecules to grams. So that's really kind of to summarize what it is we did here. And pretty much with all of these conversions, if you go back to where we were on day one, and this is kind of what you were saying, really the two conversions we need simply are the molar mass and Avogadro's number. And those are really the only two types of conversions that would take us through all of our calculations. In fact, when we started on day one on this stuff, I think that was a week ago today, we wrote down a series of conversions. And if you write down the series of conversions for any one that we've done here in Chapter 6, write it out completely. That will take care of all the conversions that we're doing here in Chapter 6, I believe. I might be lying, but it wouldn't be purposefully. Okay? Any other questions? All right. Then, this is the stuff that we're going to do next. This is the stuff that when I was a student that got me interested in chemistry. I loved chemical reactions. And if you haven't kind of realized that yet, I think we maybe did this on day one. Of course, what's in here? Or what could be in here? Hydrogen or helium. Okay? And, you know, I just can't ever have a balloon out here. You know, when us chemists sit around, oh, I gotta be careful here. When us chemists sit around, we have parties, we pass around balloons. And we fill them with different gases.
Oh, okay. You know, and we inhale gases, and we got helium here, and of course we'll do gases next, I don't know, chapter 11.
And so, this one here is a gas that is very light, but we'll also be looking at a very dense gas coming up here when we get into those gases. And we'll kind of see what effect that has on one's voice.
And you gotta be careful. Sometimes when you inhale too much, you know, my lips turn blue, you get lack of oxygen to the head and so forth.
So, of course, it's also fun to test by fire, and so we'll go ahead and test these by fire. And sometimes when I lack oxygen to the head, they get a little jittery here. And we'll just go ahead and light this up. There we go. And somewhere here I got my glasses. And this is really only fun if you turn down the lights a bit. And I got my candle on the stick, and we're going to ignite some balloons, just because. And we'll take this first one here. If you get startled easily, you might want to cover your ears. Okay. And, oh, I need to light it again. Once again, if you get startled easily, you might want to cover your ears. That's fun. I like that. Now, first one over here was which gas? Helium. Which one do we give to kids? Right, we give this one to kids. Over here, this was hydrogen. And where's a very famous event involving the explosion of hydrogen? Hindenburg. Hindenburg was a blimp that was filled with hydrogen. Came over from Germany back. This was before World War II, at least before the U.S. got involved in World War II. Their blimp was filled with hydrogen, mainly because the Allies were withholding the supply of helium from the Germans because they thought that maybe they would put it to use in blimps and so forth as a part of the war. But we saw a tragic consequence of that then in the Hindenburg. Now this last one, this is one that involves a mixture of hydrogen and oxygen gas. And in order to do this one, I do need to put some headphones, ear protection on. And I need you to cover your ears if I'm going to do this as well. So go ahead and cover your ears up. All right. And now that we've woken up the whole neighborhood, what we're going to do is we're going to actually explain what we just saw. So let's write down a statement here. And the statement we're going to write down is this. First of all, the two gases that were in the balloon were hydrogen and oxygen. So what we'd say is this. We would say that hydrogen gas reacts with oxygen gas In fact, this was the reaction that was in the last two balloons. The last two balloons were the same chemical reaction. But the last one was more dramatic because the hydrogen and oxygen were contained in the balloon to begin with. In the one over here that just was the big orange ball of fire, that one there was hydrogen reacting with oxygen, but the hydrogen couldn't react with the oxygen until what happened? The balloon popped. Once the balloon popped, then the hydrogen mixed with the oxygen. That's why you saw a bigger flame and everything, because the hydrogen was beginning to spread out from that flame. And the oxygen that's in the air is not 100% oxygen like was in the balloon. The oxygen in the air is about 21% oxygen. So it's a little bit less vigorous reaction, this one here, as compared to the last one. But it's the same reaction. So hydrogen gas reacts with oxygen to produce. And any idea what we produced in this reaction?
Energy?
Well, we did produce lots of energy, but in terms of a chemical, which chemical do you think we produced? Water, exactly. Now you're not seeing a big wet spot up here. No, no wet spot. So what happened to the water? Evaporated. Of course, it was produced in which phase? In the gaseous phase. Okay, so it's not produced as a liquid, it's produced as a gas, because of course if we heat water up, it turns from a liquid into a gas that we call steam, and that's what we see. Now in terms of chemical formulas, we now need to write the correct formulas for each one of these. If we wrote the formula for hydrogen gas, it would be H2. You might say, why is it H2 and not H? Remember, what did we learn about hydrogen? Yeah. Diatomic element, exactly. It's one of our diatomic elements. And recall that there are 7 different diatomic elements. And we had a little mnemonic for them. It was hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. And our mnemonic was Honkelbrief. Okay? And we said when we have these substances in their pure uncombined form, the most common form of these elements is their diatomic form. So when we encounter hydrogen gas, the hydrogen gas that we encounter is H2. It's not H. Likewise with the oxygen gas. If it reacts with oxygen gas, its formula is O2. Well, then we put in what are called phase labels. And the phase labels we have are G, which of course is gas, L, liquid, what else? Aqueous, which is labeled as AQ, and the last one would be S for solid. So we use phase labels in our chemical equation to tell which phases are present. Well, then we produced water. The formula for water is H2O. And the phase label we give here is gas. We did not produce it as a liquid, we produced it as a gas. So this here would be a chemical equation that shows what happened in this reaction. Now if we went back to the models and looked at this, I'm going to go ahead and take out a molecule of oxygen and a molecule of hydrogen. So we can just kind of follow what happens here. And I'll put this on the dot cam so you can see. And sometimes it takes a while. Oh, perfect focus, first time, wonderful. So now, when a chemical reaction takes place, molecules wind up colliding with each other, as they always are. But if we add some energy to it, like we did, we put a flame to the balloon, what will happen is that will cause some bonds to break and other bonds to reform. And if we wind up reforming them, we wind up with something like this. This here represents our molecule of water, but it turns out we have some leftover parts. And those leftover parts are not shown in our chemical equation. So that must mean that there's something wrong with our chemical equation. If we come back here, again, there's something wrong with the chemical equation because the chemical equation is not showing these leftover parts. And one of the things that we talked about earlier this semester was the law of conservation of matter. And the law of conservation of matter says you can neither create matter nor destroy matter as a result of a chemical change. Now, if we didn't mention at the time, a chemical change and a chemical reaction are the same thing. So when we talked about chemical change and physical change, a chemical change is a chemical reaction. So again, there's something missing. This here does not account for all of the particles that we have shown at the beginning. So what we're going to do is I'm going to change this equation, and I'm going to put a number 2 in front of the H2. When I put the number 2 in front of the H2, what that means is this. It means that I have 2 hydrogen molecules. And let's see if I can find everything here. There we go. So we got our 2 hydrogen molecules, and we've got our oxygen molecule. And right now, that's what our equation is showing. It's showing the 2 molecules of hydrogen and the 1 molecule of oxygen. So again, once a chemical reaction occurs, we'd put into something energy like the flame that we did here. Molecules are going to collide with each other. When they collide, some bonds will break, and other bonds are going to reform. So as we start putting the pieces back together here, what you're going to notice is, pretty soon, we're not going to have any spare parts left over. What we are going to have, though, is 2 molecules of water that are formed. And again, how many spare parts do we have? None. And if there's no spare parts or spare atoms left over, what that means is we've, in essence, balanced the chemical equation, and it conforms to the law of conservation of matter. And so now if we were to read this, what this means is 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. So again, the way that you would read that is 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. Now the numbers that we put out front are called coefficients. So again, the coefficients here shown in red. Now, where have you used coefficients before? In math. And specifically where in math? What does it stand for in math? Where are they written in math? Anybody? What is a coefficient? Number that's outside. And where do we usually put it? In the front. So if we wrote something like this, 2x, 2x means what? 2 times x. It means 2 times x. So we write 2x, we put it there. We do not write it like this. We don't write x2, we write it as 2x. So coefficients always go out at the front of the formulas. Likewise, if we had multiple atoms in the formula, we didn't go ahead and balance this by putting a 2 somewhere in the middle here. The 2 winds up going out at the very front of the formula. So we don't write x2y, though it would mean the same thing. Actually, in chemical equations, it doesn't. We always write it as 2xy, where the coefficient goes out in the front. And just like in mathematics, where it stands for multiplication, the same is true over here. So if we wanted to know the total number of hydrogen atoms, the total number of hydrogen atoms that is involved would be 4. Because there's 2 times 2, or a total of 4 hydrogens in there. And we can see that by the 4 white ones here. The white ones representing the hydrogen. There's 4 hydrogen atoms that are present in the molecule. Okay, now some other terminology. Any questions here yet? Okay, some other terminology. Those on the left-hand side of the arrow are called reactants. Those on the right-hand side of the arrow are referred to as products. So reactants are what exists before a chemical reaction takes place. The products are what exist after a reaction takes place. And that should make total sense. Because if you worked in a factory, the final thing that's made is called a product. So again, if you're making something, maybe you're in crafts or whatever, the product is what you make at the end. It's the stuff that you sell or you give away. So again, it's what's present there at the very end of the reaction. The final thing that we have shown here, this final chemical equation, is referred to as a balanced chemical equation. And a balanced chemical equation is one that conforms to the law of conservation of matter. So again, a balanced chemical equation is one that conforms to the law of conservation of matter. Okay, let's go ahead and look at another one. And this is another one that we may have already looked at in here, but we're going to look at it in a different context now. And in this one, and I'm going to dim the lights down in just a bit, we're going to start with some magnesium metal. I guess I'll put it out on the dot cam. We'll take some magnesium metal, put it out here, and we can see that the magnesium metal has that metallic luster. And what we're going to do now is we're going to ignite that magnesium. And have we seen this one before? Yes or no? Yeah? Okay. We're going to look at it in a new context, but I'm looking for my fire. There we go. So we'll go ahead and start up the flame. And then what we're going to do, use some tongs. Here we go. And now we're going to turn down the lights so we can look at this. And if we watch this, we want to kind of watch it a bit off to the side and not directly. And I'll try to get this under the dot cam here. So we see now that this is reacting very brightly. There we go. And one of the interesting things, if I did not mention this before, about magnesium is magnesium used to be used in flash bulbs. And back before we had things like smartphones that everybody having their own camera and flash built in, we had single-use flash bulbs, and those single-use flash bulbs were filled with magnesium wire. And then we would take a picture of it. There'd be a tiny little battery in there, a little charge, that would go ahead and ignite that magnesium wire. And then, of course, you saw it was a very white color. And so white, when you're doing photography, of course, is going to be very good because it gives very pure colors. And then they were developed, and we would tell that the flash bulbs were used because the plastic cover on them would melt, and so they were single use. We come back here and look at the product. We can see that the product that we get out of this is going to be kind of a white powder. So now, we want to write a chemical equation for what just happened. So let's first put this into a word description. What did we start with? Magnesium. And which phase was the magnesium? Solid. So let's write out the words for this one first. We would say that solid magnesium reacts with. Now this is where when interest students kind of have a little trouble getting going. What is it that it reacted with? Some are tempted to say fire, but fire is not a chemical.
There's a heat.
And heat is not a chemical. Reacts with oxygen. So the heat is the energy. The fire is the energy that's provided. But it reacts with oxygen. And of course the oxygen is in which phase? Gas. And then we'd say to produce, and the stuff we made, not a whole lot of options. If we make it out of magnesium and oxygen, it's going to be, what would we guess?
Magnesium oxide.
Magnesium oxide. Yes, it is not complicated. We just put together the two elements and we're making magnesium oxide. So now, if we want to write out a chemical equation for this, we start off with the magnesium. The formula for magnesium is going to be Mg. And should we put a 2 after it? No. And why should we not? It's not one of the diatomic elements. Remember, these are your diatomic elements. Magnesium is not one of those diatomic elements. And the phase label would be solid. Then we react it with oxygen, which has a formula of O2. Phase label would be gas, the G. And then we make magnesium oxide. Formula for magnesium oxide would be MgO. I know many of us want to say 2, but it's not 2. And the reason why it's not 2 is because we need to go back to where they're located on the periodic table. Magnesium is Mg with a charge of how much? 2 positive. Oxide is O with a charge of 2 negative. So if we have Mg with a 2 positive and O with a 2 negative, what happens to the charges? They balance, they cancel each other out. So the formula is simply MgO. The phase label we'd put in here is, we didn't label it, but what is the phase here? This is a solid. So we reacted to produce magnesium oxide. I'll write it out here in the problem. This is magnesium oxide solid. And so label it with an S. Now this equation is not balanced. It is not balanced. So now we'd like to balance this chemical equation. When we balance the chemical equation, we cannot change the subscripts. In other words, we can't just go ahead and erase this one and say it's balanced, because now we changed from the diatomic form to something that, well, does exist, but is not very common. And likewise, we can't balance it by putting a 2 down below here. So that doesn't work either. When we balance chemical equations, what we're doing is we are changing the coefficients. So we need to change the coefficients, and we work about it in a systematic way. So it goes something like this. First of all, we look at the magnesiums on the left, magnesiums on the right. How many on the left? 1. And on the right? 1. So we'd say that magnesium is balanced. Then we go to oxygen. How many are here?
2.
And how many are here? 1. Well, now they're not balanced, and how many do we need altogether for oxygen on this side then? 2. So the way we balance that is to put in a coefficient, and the only place that coefficient can go is in the front. Remember, we don't write x2y, we write 2xy. So coefficients always go at the front of the formula. Of course, now that we put the 2 in front of here, we now have how many magnesiums? 2. So to balance the magnesiums, we need to put a 2 in front of the Mg. At this point, this is a balanced chemical equation, which you should check. We have 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens, because of course remember that a coefficient means that we are multiplying the result. So any questions on this one? Okay, let's try this one here. I don't have a demo for this one, though it would be fun if I did. This one here reads nitrogen gas. Reacts with hydrogen gas to produce gaseous ammonia. So now with this word equation, a word description, we're going to write out an equation. To write out the equation, we need the right formulas. Nitrogen gas is going to be N2. It's going to be N2 because nitrogen is one of the diatomic elements. The phase label is going to be G. Reacts with hydrogen gas, which would be H2. It's H2 because, again, hydrogen is one of our diatomic elements. And the phase label there is a G. Then we're going to make ammonia. And I know we've mentioned it now at least once in here. This is one of those chemical formulas you're supposed to memorize. Formula is NH3. And you say, oh, I thought it was NH4. Well, if you're thinking of NH4, that's NH4 with a positive charge, which is called the ammonium ion. And I might actually be getting you guys confused with my other class. It's a little higher level, and so we've gone through this. But if I have not mentioned already, you need to know that ammonia is NH3. It goes by its common name. We don't call it nitrogen trihydride, just like we typically don't call water dihydrogen monoxide. So ammonia goes by its common name. Now at this point, we'd like to balance the chemical equation. I passed out here before class began today, well, not before it began, but while you were working on your problems, a list of strategies for balancing chemical equations. Now, what this is here is a list of strategies. It's not a list of rules, but it's a list of strategies. The reason why it's a list of strategies is because when we balance chemical equations, we're using a method called balancing by inspection. Our technique is balancing by inspection. And what balancing by inspection is a fancy name for trial and error. You try something, if it works, great. If it doesn't work, you try something else. That's really what we're doing when we balance chemical equations. But these are some strategies to reduce the number of trials that you have. So as we go through them, they are kind of applied in order. When I say in order, then that means that you should think about them in the order that you see them. So the first one says, if you see an element that is by itself or an element in the simplest formula, we should balance that one last. Second strategy is to use the least common multiple to balance the number of atoms on each side of the equation. So that's one of them we could do here, is a least common multiple. So for example, if we're looking at the hydrogens here on the left, hydrogens on the right, what is the least common multiple between 3 and 2? 6. So that means that on the left-hand side, we're going to have to get 6 hydrogens. What number do we need to put in front of here to get 6 hydrogens? We need to put a 3 in front of here. And then on the other side, to get 6 hydrogens over here, what number do we need to put in front here? We need to put in a 2. So if we put in the 2 here, 2 times 3 is 6. Here, 3 times 2 is 6. Of course, then if we look at the nitrogens, we see 2 nitrogens here, 2 nitrogens here. This is a balanced chemical equation. Now, some of us are going to have an easier time. This is a strategy that is sometimes used to make a table. And the table would look something like this. And I'm going to put this in black. There we go. And in here, I'm going to look at the reactant side and the product side. And I'm simply putting this line here to coincide with this arrow, because this is the reactant side, this over here is the product side. And then we're going to show the 2 elements that are present. And the two elements that are present here are nitrogen and hydrogen. So it's a way to kind of keep track or tally what you have. So before you even begin balancing, one of the things you can go through is to count the number of nitrogens and hydrogens on each side. We look at this one, we see how many nitrogens? 2. How many hydrogens? 2. On the product side, how many nitrogens?
1.
And how many hydrogens? 3. So you can kind of make some tallies, some marks like this. Then the whole idea is to make the number of marks of each element the same on each side. So last time I started with hydrogen. I could, since these are equally difficult, we could start with nitrogen. If I see 2 nitrogens over here, and on this side only 1, what number could I put in front of this to make the number of nitrogens equal? 2. So I'd come in here and put a 2 in. Once I put a 2 in front of here, then I'm going to remark and retally. So how many nitrogens do I now have? 2. Then I look at the hydrogens. How many hydrogens do I have?
6.
And so I go through and mark the 6 hydrogens. Now at this point we can see we were successful in balancing the number of nitrogens. We now want to balance the number of hydrogens. We see we have 6 and 2. That means that the number we need in front of here is
3.
a 3. And we put it in just like this. And would have the 6 hydrogens. So if it is useful for you to tally these, then go through and tally the elements. Okay, any questions on these here? Okay, let's practice these, and these will be coming up on the Socrative app. The ones we're going to balance. Balance these equations. And by the way, we do not always need phase labels in them. And the ones I'm writing here now will not be showing phase labels. So they will be V plus O2 makes V2O5. Next equation we'll look at will be Al plus O2 yields Al2O3. And then the last one will be this one, KClO3 yields KCl plus O2. Now what you're going to find helpful here if you're beginning, if you're a beginner like many of you are, notice I'm doing them in 2 colors. I'd recommend doing them, if you can, in 2 colors, or maybe one in pen and one in pencil, because once I put something in this color here, these subscripts can't be changed. You can't erase them, you can't add to them. The only thing you can change in your balance is the coefficients. All right, so I'll give you some time here on the
Right?
This is how you're going to see them if there's a multiple choice question. The Socrative app are worded in a way that you can see them on an
You
exam.
have 1 KCl. I think you have 1 over here. For your number 3, you mean? I'm gonna, yeah, I put 2 in front of that. 6 on 2 KCl.
You can keep talking. That's all right. Just keep talking. Explain.
3 in front of that.
You had to double check.
I think maybe once he explains it, though, okay.
I'll give you about 30 seconds to get this first one in. And you can keep talking if you're looking at the later ones. Just read the question carefully. Okay, we'll do a quick check on the answer. Count down 5, 4, 3, 2, 1. The correct answer here is a 5. when we talk about the coefficient on the O2? It's a 5 because if we went through and balanced it, the coefficients are from left to right. Help me out. 2? I don't think it's 2, is it?
4.
4. Then 5, then 2. So we check the quick balance. There's 4 vanadiums. 2 times 2 is 4 vanadiums. 5 times 2 is 10 oxygen. 2 times 5 is 10 oxygen. So again, if you pay attention to the wording, if you saw this as a multiple choice question, the way you're seeing it here is a way that it could appear on the exam. Now, some of you may have had coefficients that looked like this when you balanced it. You may have had 8, 10, and 4. This equation is balanced because there's 8 vanadiums, 20 oxygen, 20 oxygen. But what can we do with all of these coefficients? Divide by 2. So when you're doing mastering chemistry and so forth and looking at answers in the back of the book, they're always reduced to the lowest whole number ratios, which in this case would be 4, 5, and 2. Okay, here's another way that the problems can be worded. Read this carefully. Now we're looking for the sum of the coefficients. If they're reduced down with the smallest whole number coefficients, what is the sum of your coefficients? Remember, if we don't write a coefficient, the coefficient implied is a value of 1. Just like we wrote NaCl, it means there's 1 sodium and 1 chlorine. So get your answers locked in. We want the sum. And we will count down on this one. 5, 4, 3, 2, 1. Correct answer is 9. And it is 9 because the coefficients from left to right are, help me out, 4, 3, what the heck? Sometimes that happens, and I don't know why that happens here. They go, oh, there they go, 4, 3, and 2. Okay, last one. Go ahead and get them locked in, please. When balanced with the smallest whole number coefficients, the coefficient on the KCl. So look at your equations. When balanced with the smallest whole number coefficients, the coefficient on KCl is. I'll give you 10 seconds. 5, 4, 3, 2, 1. Answer here, great, is a 2. And it is a 2 because from left to right we have a 2, 2, and 3. Okay, we're going to end with a demonstration today. The demo we're going to end with is the decomposition of hydrogen peroxide. In fact, it's called the catalytic decomposition of hydrogen peroxide. And we can write down some formulas here for this. What I'm putting in here is some hydrogen peroxide. You're not expected to know this formula, so I'm telling it to you. Formula for hydrogen peroxide is H2O2. H2O2. And this stuff is dissolved in water. If it's dissolved in water, the phase label we put after the H2O2 is?
Aqueous.
Aqueous, AQ. So we're going to go ahead and put that into here. Then, what we're going to do is we are going to take a catalyst, and now the catalyst is not placed into the equation as a reactant nor as a product. So, I don't want to put this in red, I want to put it in black. So I have H2O2, aqueous. The catalyst we're using is manganese 4 oxide. That's a manganese 4 oxide catalyst. Now a catalyst is a substance that does what? Anybody know from your previous exposure? It's a substance that speeds up a chemical reaction. And what is the caveat? The caveat is without being consumed. So it's a substance that speeds up a chemical reaction without being consumed. And a catalyst we write above the arrow right here. The catalyst is manganese 4 oxide. So what does manganese 4 mean? It means Mn with a charge of 4 plus. Oxide is O with a charge of 2 negative. So the formula for manganese 4 oxide is MnO2. It's MnO2. So we write it above the arrow like this. Okay, now I'm going to take this manganese dioxide. I need you to close your eyes. Make a wish. Okay, you can open up your eyes. And your wish is granted, so saith the genie. All right, so now we want to tell what happens in this chemical reaction. What happens in this chemical reaction is the hydrogen peroxide decomposes to yield. Here we go, hydrogen peroxide decomposes. We should say in the presence of a manganese 4 oxide catalyst to yield, and the products that are produced here are water and oxygen gas. So oxygen is produced as a liquid. If we don't put a phase or refer to the phase, water may be assumed to be a liquid. So how would we write this in the equation? Water would be H2O. Phase label would be liquid, L. And oxygen would be O2. Phase label would be G. So now, when you balance this, what you're going to ignore, I just erased the catalyst. I'm going to put it back in there. When you balance it, this is the equation you're balancing right here. The catalyst does not at all affect how it's balanced. So you basically ignore the catalyst when you balance it. So balance this equation, and this equation is what we're going to start with on Tuesday. You must have this equation balanced when you come in here on Tuesday. It'll be the first question on the Socratic app on Tuesday. Any questions?